Hello, good morning. All right. And um, I have to pre record this lecture because there was the schedule crashes with the Thursday morning class. So that's what it's supposed to be, right? Okay. So this is the last topic before the midterm. So that means I am going to reserve next week's class to be a review. Sounds good? Yeah. All right. So that means after this lecture, I will distribute a set of exercises that you can try, and you have a chance to go through those and practice solving problems. And we'll have times next week to go through some of those problems together. Or even if you have any questions that you would like to ask before the midterm, that would be good. So that means, according to the handouts, we are going to include up to this lecture number 6. Okay, so the lecture number 7 turns out to be a review for the midterm. And the lecture number 7 on this one, I mean, on this particular handout here, is going to be lecture number 8. That will be after the midterm. Okay, sounds good? Okay, so that's what we agree with the other section, that we're going to draw the line in terms of the amount of contents up to lecture number 6. Okay, and we'll move on to other stuff after midterm. Okay, all right. So the last topics that we're going to cover before the midterm here is the vector values functions. And it's just the development that we have already been built up to this point so far. We kind of like, okay, understand the parametric equations. We understand how to incorporate some vector into it. We have done some, sort of like operations between vectors, dot products, cross products, the utilities of those, using it to calculate some geometrical problems, understand the meaning of it geometrically, and then you apply those to build some extra stuff. So this is going to be another things that vector can help us. Okay, so that's why it's the purpose of this lecture right here is the vector valued function. So we're going to turn some functions that we already familiar with using, like, f of x, f of y, on, but now we're going to turn them into vectors instead of just like pure numbers, and we'll see what it means by this. So up to this point, everyone seems to be okay with this parametric curves, yeah, right? And then we just just give me a parameter t, and then we can, what we have been talking about was just thinking about t to be time, for example. So time keep increasing, keep walking. I mean, time's always increasing. So we can use that time to be your parameter, and then your parameter is just, change the value of, if it's in 2D, you have x as a function of t, y as a function of t. If you have in three-dimensional space, you have x, y, and z. They are all can be represented under function of t. Now, what if, just like what we did last time, we're going to turn this stuff into something that's going to link to vector? How would that be? All right, let's take a look at this. So let's start from the example number 1 here. You have a parametric equations that looks pretty good. It's just a straight line because they all depends only on t. Yeah, so they are all linear in t. So when everything is linear, it means you're going to get just a straight line. Let's take a look and see how it goes. So I'm going to draw, okay, let's give like an axis. Okay, I'm gonna draw it nicely here. Trying make it nice looking. Okay, here we go. Okay, that's x, y, and z right there. Okay, so x is here, y is there, z is there. So let's start from some spot that's kind of easy to sort of place on the x, y, z coordinates. So let's start from t equal to 0. Why not? So let's say at t equal to 0, your x, y, and z coordinate is going to be 1. Yeah, just substitute 0 into the value of the t. y is going to be 0, z is going to be 0. So your starting point, if you start everything from 0, is going to be on the x-axis, x equal to 1. So let's say the scale is somewhere around, well, let's give it like somewhere around here. All right, so 1 is right there, 1, 0, 0. That's time equal to 0. The point that we are talking about is that red dot position right there. Now let's move on to some other times, maybe some other points that's kind of easy to spot. Let's move one step. T equal to 1. So now x equal to 0, y equal to 3, z equal to 2. So that means at t equal to 1, you are at 0, 3, 2. And where is that? It's going to be 3 on y. So let me use about the same. I'll try to draw in the same scale right here. 1, 2, 3. 1, 2. So it's going to be here, right there. There. That is your t equal to 1. Okay, cool. And we kind of know that going from 0 to 1 in parameter t is going to trace a straight line because we already discussed this is just a parametric equation of a straight line. So let me draw like a nice line for you guys. Nice. I hope it's nice enough. Here we go. And actuality, you don't need to start everything from 0, right? So that means what you can actually do is you can go all the way. It's just representing a straight line. That is the blue line that I just placed right there. So this is what we learned maybe probably first time we see each other. We talk about this parametric equations. Oh, that was like months and a half ago, yeah? That's when we first met and we talk about parametric equations like this. Now, what I am going to do now is I'm going to place a vector into this. How? What do you think? How I'm going to be able to do it? Well, Ajahn, this is easy because what we did before was, here, think of it this way. Every time you have a position in an x, y, z coordinates, I can turn that into a terminal point of a vector. You guys with me? So that means this one can be turned into vector 1, 0, 0. What does this mean? It means this vector, if I start everywhere, I mean everything from the origin of the coordinates, this 1, 0, 0, the point 1, 0, 0 will mean the vector starting from origin or 0, 0, 0 and pointing to 1, 0, 0. So that means it's going to be a vector pointing this direction right there. Okay, let's do it one more time. So to 0, 3, 2, if you turn this into a terminal of the vector, it's going to be, I put it in a bracket instead, right? So when you have a point, it's just a parenthesis, วงเล็บไม่ใช่ but when they turn it into a bracket, that is the vector. Because this is a 0, 3, 2, so if you start everything from origin, then it's going to be the vector that point towards that orange dot right there. But you start seeing something now. So that means I can trace this straight line by looking at the endpoints or the terminal points of vector. So think of it this way. So I'm just like, hey, I'm gonna point here, there, here, 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 point there. With me? So what I'm doing here is just like, hey, wherever that terminal of that vectors is, that is the point on the line that I want. So once I keep doing this, doing this, doing this, doing this, doing this, doing this, so that means all I need to do is just I can re-represent everything in terms of vector. So what I'm saying is, hey, I'm just gonna take all these parametric equations, put them into a vector. 1 minus t, 3t, 2t in the bracket. Lecture นี้ง่ายไปไหม Right? That's already good. That's a vector. But eventually you accomplish the same thing. You can use that vector to trace a curve. And this is the vector values function pretty much. It's a function that is represented in terms of a vector. Try again. Example number 2. All right, everyone try together. Describe the parametric curves represented by the following parametric equations. A and C are positive constants. Okay, so this one is a good practice actually because we are going to face a lot of sine and cosine t like this. We actually have already done that a couple of times. So why not do it again? Okay, so I'm going to draw once again our axis here, the x, y, z, just like before. Okay, so just to practice, do you guys remember what is this parametric equation? We have seen this many, many times. If you don't care about the z components at this point, you're going to look at a circle of radius a. You guys remember that, right? A cosine t give you the x components. A sine t give you the y components. So why not? Just by looking at the a, x, and y coordinates, what you're getting is just a circle of radius a. That's good. Okay. But then, well, Ajahn, wait. We are not trying to do anything just on the xy plane. You have the t times a constant c in the z components. So as the t increases, the elevation, ความสูง yeah, the height along the z axis is going to increase along with it. So what does it mean? It means, okay, think of it this way. I want to sort of build this whole thing step by step. So if you still don't have the z components, what does it mean? Okay, let's forget about this c components for a while. Okay, but I'm gonna still have it, but let's forget about it for now. So what you're looking at, a cosine t and a sine t, I can turn this to, put them in a vector format. You guys with me? So that will be just like the example number 1. You are tracing a circle, but you're using the terminal point of this vector to trace that. So what I'm saying is this is what you did. You're starting from t equal to 0, cosine 0 is equal to 1, sine 0 is 0. So you're starting here. That is point A 0. But at time equal to 0, okay, let me put it on the side here. It's a 0. But now you can say it's a vector that's point towards. Okay, let me use the green one so it's a little bit easier to see. Here. See? This green right here is a 0 vector. And what I'm having right here for this parametric equation that being put in a vector form is you're just having this. So this vector is just going to rotate around. And the terminal point of these eventually going to trace a circle. You have to do this continuously. So eventually you're going to get a circle. With me? Very nice. I hope you're with me. Right. There's no answer because I'm recording on my own. All right. But then now when you're considering the 3 components, right? I mean, it's a 3 space. So you have a cosine t, a sine t, ct. What does it mean? Now you add the z component to it. And what does the z component does is lift the whole things up. So not only it circulate on an xy plane, no. Every time that you circulate, you have the increase or the changing of the z value in higher value. So it means you are increasing the elevation. มันยกตัวขึ้นเนาะ So you can think of this like at first you have a circular motion, but then you want to extend this along the z axis. What are you going to get? พวกเราทุกคน what are you getting? Of course, you're going to get the helix right there. With me? And that increase there, you just have the z component of the whole thing. That is the z component equal to ct. Yeah, that's the whole idea. But now I hope the reason I spend so much time with this slide because I want you to just get this point. So what I'm doing right now is just, hey, see, I'm just having a vector. Let's try to point, point, point. Just keep pointing. โหเริ่มเลอะเทอะ So the endpoint of those vectors representing a curve นั้นจะว่าไปแล้วพออาจารย์ทำนิ้วอย่างนี้เนาะ it's like when I'm doing my finger like this, my finger actually is my vector, the tip of my finger, that is the terminal point of my vector. So if you look at just at my tip of my finger, I'm tracing a helix with me. But I mean, without my finger, you don't have the vector, you just have a curve in a helical form. That was parametric equations that you had before. But now with the finger, you just have the vector that's pointing onto the curve. เฮ้ยรู้เรื่องไหมโอเคนะพอได้นะ all right, so in terms of the operation, it's so simple. If you have a set of parametric equation like this, all you need to do, just wrap this, put them in a bracket. And now you can choose, you can do it in a bracket form or you can do ijk. It doesn't really matter, they're all the same. However, what I'm saying over here is now you are representing a vector, and this vector is bam, is a function of parameter t, and that is vector valued function, yeah, of a real variable. Of course, that's what we use, that's the real value t. And simply, instead of talking the whole sentence right here, just say that is the vector values function. And from now on, every time you see this, a vector r that is a function of t, you know in your head, you have three components in tree space: x as a function of t, y as a function of t, z as a function of t. So these are just component functions, or just simply say components. We use that in physics, we use that in vectors, we have been using that. But now is the components of your vector values function. See, so the business that we are doing here right now is just pretty much nothing new at all. You just have to accept it, the utility of vectors. Our vector มาใช้ Very nice. So let's try it again. Describe the graph of the vector value functions that you are seeing over here. บอกให้อาจารย์ this is exactly the same now, because when you see this, บอกอาจารย์ cosine and sine again, with the factor in the front is now number one. So that means this is just a unit circle. But then you see that there is a t, the elevation along the z-axis. So once again, you are looking at the parametric equations along, I mean, in the x and y and z points. But this eventually going to trace a helical curve again with the radius 1. อาจารย์เริ่มขี้เกียจวาดสวยแล้ว but I hope you guys see what I'm doing here. All right. Okay. Let's do it one more time. Right there. There you go. Okay. And the radius at this point is now just 1. Right there. Just 1. Okay. Very good. Nice. Keep going. Okay. Try again. So when I say try again is, there might be a wordings that talk about the characteristic of this vector value function. For example, you have heard of domain before in function. So it's pretty much the same thing here in the vector values function. So all you need to do is just all of the allowable values of the parameter t. Okay. That is your domain. However, because now you have three components though, right? You have x, y, and z components. So you have to take into account the intersections of those domains in x and y and z. The reason you need the intersection because you just have to take the smallest set possible, right? Because if there is some exceptions in y-axis, in z-axis, so that's not good. So all you need to do is just you want to take the smallest set that you can satisfy both x, y, and z components of your function. That's all. So that's why you need the intersection of the natural domains of the component functions. grab the x, grab the y, grab the z, analyze the domains of these x, y, and z, and take the intersection between them. Okay, that makes sense เนาะเอาเฉพาะ area ที่มันเป็นจริงได้หมดทั้ง3 components. That works. Okay, let's give it a shot and see if there was a questions about what is the domain of this, the domain of that. All you need to do is just try to look at the domain of possible values of t. For example, let me zoom in here. This exercise say find the domains of this function and evaluate the value of this function at particular point t naught. So evaluating is not too bad. So if you want r at pi, all you need to do is just substitute the value in there and then you're done. So it's going to be cosine pi and minus 3 pi, right? So evaluation is not bad. But now if you want the domain, all you need to look at is, hey, look at the x components. What are the possibility of the t here? What are the allowable values of t? And when you look at this one, Ajan, it's just a cosine of t. So there's no restriction on t. So that means over here, what you can say is the possibility of t over here is just everywhere. With me? Right? T is just a member of any real number. Or you can say it's just real number if you want. That is fine too. But then when you look at okay, let me put it here. 3t, same thing. There's no restriction on this. So t on this one also everywhere. So now you do the intersection between them, and that will give you the net domain of this r. So the total domain of rt is just everything. Yeah, simple, something like this. Okay, let me give you a contrast with the next exercise right here. So let's consider the second one. Well, now Dan, we have some problem here. When you look at this, you know that everything that comes under the square root has to be positive. Otherwise, you're going to end up with the imaginary numbers, which we are not looking at it at this point. So what you have over here is 3t plus 1 must be greater than or equal to 0. So in this case, you know that from the first component, the domain of the component function, the x component function over here is just t must be greater than or equal to negative 1/3. Leave it there. Look at the second component right here. Well, Dan, there's no restriction on t squared. T can be anything. So in this case, t is just everywhere. Now you do the intersection between them. So what is it? The domain is, of course, anything that go beyond minus 1/3 all the way to positive infinity. So that would be, let me use a bracket here. That means, sorry. I take this 1/3 all the way to positive infinity. Keep writing it wrong. Okay. Not bad. Okay. Evaluation of this vector value function is going to be a straightforward manner. If you want r at 1, all you need to do is just substituting this thing in. So it's square root 4, 1. So it's just 2, 1, for example. Not bad. All right, let's do one more. What about the last exercise right here? The one in the bottom. Okay, start from the x component. Look at this, but John, that is quite all right. First, you have exponential. And for the exponential, there's no restriction on t. So at least for this one, I can say t is just anything. That is good. For the inverse sine, because everyone knows the sine of something has the value between negative 1 to positive 1. So the inverse of the t actually giving you the angle, right? So in this case, what does it mean? So this one means, okay, let me use this. So the t must be ranging from negative 1 to positive 1. Okay, that's good because that is the inverse of the t. So the t in here has to be somewhere between -1 to +1. Those are all possible value of sine of something. Yeah, must be equal to somewhere between -1 to 1. Yeah. Okay. Okay. And the last component, this is a tree space. Okay, let me pop it up here. Now you have a natural log of 1 minus t. So the argument 1 minus t for the logarithmic function has to be non-negative. And it's not allowed 0 in it. So that means the argument of this natural log has to be positive. So that means the requirement of this one is 1 minus t must be greater than 0. Okay. Or that means in this case, t must be less than 1. Okay, nice. All right. Now, once we have this, you have to intersect them all. Okay. Because the first one is pretty much everywhere, so it does no good. So pretty much you have to look at the intersection between the y components function and the z components function. Okay, as you can see from this one, that this one allow you from -1 and up to 1, but this one is just 1 and below. So after the intersection, what you're getting is your domain is -1. You take it, so I put a bracket in there, but you have to exclude 1. So I use just the parenthesis right there. Cool. All right. And evaluation is always simple. If you want to figure out r at 0, you just substitute the value in there. So it's going to be 2 e to the 0 inverse of 0 and log of 1. Not bad. So at the end, if you want, it's just 2, 0, 0. All right. So I hope you see the, well, you can say the similarity and the differences between just a regular function that what you have been learning since middle school and the vector values function. It seems like it's just a straightforward extension. You just take, you know, the function and plug it into the components of a vector, and each component is just x, y, and z. That's it. And then you already had the vector values function, and then you can determine the domain just like you did before, except you need to do the intersections between all those components. All right, keep going. So once you have that, now from now on, you know how to sketch a graph of any given vector value function r. Okay, and the key is you should be able to tell the directions as well. We studied this since the first time we met, talking about the orientation or the direction of a parametric curve, right? So every time you have to pretty much you trace a curve or whatever it is, you know the direction that we named this an orientation. So it's pretty much the same thing, even though we use the vector representation, but the meaning of the curve stays the same. So start from the first one, guys. ลองดูหน่อยไหม Give it a shot. Why not? Here we go. I'm gonna draw. Okay, I'm just doing. This is just an XY component, so I'm just gonna use two-dimensional stuff here. Okay, so it seems like for this one, the X component is fixed. Cool. Add 2. So let me put 2 in there. And the only changing stuff is the Y components of this one. It's because it's just T. So that means as T is increasing, the value of the Y also increasing. This is just an X. This is just your Y axis. So it means the point that this vector is trying to point to is this. At t equal to 0, okay, let's just give you an idea. T equal to 0, the vector is 2, 0. And that is this vector right here. At t equal to -1, let's give some negative number, is 2, -1. So it's just 2, it's still 2. So let me sort of give you a line of sight here. That's x component equal to 2. But then y is -1. So let me put it down here. There. It's this point right here. And let's try something upward. T equal to 1 is going to be 2, 1. Up there. So you start seeing the dynamics of this one. I'm going to do this one more time and then I'm going to not doing this anymore. I think you guys kind of get bored of this. So this is your vector, 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 vector. And just keep pointing on this terminal, so at the terminal points, if you draw those dots in a continuous fashion, you're going to get a straight line. Not so nice. Okay, let me give you a nice straight line. Here we go. So that is your sketch of this graph. It's not so nice, isn't it? แหมอาจารย์ก็อยากจะวาดสวยๆบ้างนะ okay. Give me some time here. Here we go. There you go. That is your curve. All right, so I hope this sealed the deal here. You know what the vector value is. Vector value function is trying to do. Okay, but eventually you get a line. And as you can see, we start from the negative one that's below. And when you increase the t, it's moving up. So you can put the direction to it. There you go. It's pointing upward. Okay, cool. Try again. Just one more. So this is like for fun, more like a curve sketching pretty much. You have two-dimensional stuff again. Okay, and because you can see that they are just linear function in t, so you're going to get a straight line for sure. And the way to do this, you don't have to draw those vectors anymore. What I'm going to do is just, I'm going to take a shot of something. For example, there are so many places that you can sort of place the value of t into it. For example, that the things that we always do is this. Put t equal to 0. You don't know what to do. Just take t equal to 0. So the vector or the point that you're looking at is going to be negative 4, 2. Ooh. So it's negative 4, 2 somewhere. So it's going to be maybe 1, 2, 3, 4. Just give you some scale right here. 1, 2, 3, 4, 5, on and on. So this is just like just for fun. So at t equal to 0 is negative 4, 2. So I can place a dot right here. Negative 4, 1, 2, 3, 4, and 2 is right here. There. Okay. And now you can pick a point somewhere. You can try t equal to 1 that's increasing in t. So once you place t equal to 1 in there, so it's negative 1 and 8. Whoa, that's somewhere up there. Maybe I have to use a smaller scale here. Sorry. Okay, negative. Okay, let me call this like a scale of 2 then. So it's negative. Here we go. So let me call this negative 4, negative 4, 2. Dot. Okay, right there. Okay, so negative 1 and 8. So it's going to be negative 1 right here. And then you go up 8. It's right there. That's negative 1, 8. See that? I'm just interchangeable between the coordinates of a point, which is just a parenthesis. Or I can talk about this in terms of the vector that point towards negative 1, 8. So which is this one right here. I'm just อาจารย์พูดซ้ำๆไม่รู้เบื่อป่ะนะแต่หวังว่าคือเพื่อให้เราทุกคนเข้าใจเนาะว่า what we are doing over here is it's a two representation of the same thing. All right, but from this now you can pretty much conclude what kind of line that are you getting. อาจารย์ of course is going to be this straight line right here. And because you're moving from t equal to 0 to t equal to 1, the dot is going up sort of diagonally up. So you even can tell that the direction of increasing t is diagonally up that way. โอเคเนาะมันหลายๆคนก็เริ่มเห็นแล้วว่าอาจารย์ is it gonna be the question in the exam like trace a curve here. Maybe, I'm not sure, but I think it's very doable. It's very, very doable. Okay, try two more, guys. Ma, I'll give you like 2 minutes to try this. In the meantime, I'm gonna draw something here. Yeah, just like once again, X and Y. Okay, what is going to be this curve right here? Can you imagine what this is? It's 1 plus cosine t in I component, in X component, 3 minus sine t, that is in J, which is the Y component. And T go one full cycle. What do you think this curve is gonna look like? Very good. First of all, you see the cosine and sine, you know it's gonna be a circle. However, this one being added a little bit. In X, there is 1 added to it. In Y, there is 3 added to it. Plus, there is a negative sign in there. So first of all, it's going to be a constant 1 in X direction and 3 in the Y direction. So if I draw it like this, 1, 2, 3, 4, here, 1, 2, 3, 4, 5. So at least I always have 1 here and 3 there. So at least that is my 1, 3 point. Okay, that is 3. That is 1. But then around this point, I have something circulating around. You guys with me? Cosine t and sine t, that is a circle of radius 1. The coefficient or the factor in the front is just 1. So that gives you the radius of this circle. So it's just a unit circle. Oh, nice. So what I'm having over here is just going to be a circle of radius 1. So let's see if I can draw this one nicely. Oh, what did I do wrong here? Here we go. All right. Oh, pretty good. Okay, not bad. Here we go. So the only thing left is, now I know this is my curve. It's going to be a circle of radius 1. Center has been shifted to 1, 3. However, the last stuff that we need to be careful with is, hey, is a negative sign here. So that means the orientation or the direction of this is going to be clockwise. With me, guys? Because we already familiar with cosine t and sine t, it's a counterclockwise circle. So this one, you go negative sine t, so you go down first. Okay, when you increase the t, the y component lower in values because you have a negative sine t there. So that's why it's go down and up. And this. So this is your orientation of circle right there. ไม่รู้อาจารย์จะวาดทับไปทำไมเนาะมันก็กลมสวยดีแล้วเนาะ All right, very good. All right, and the one on the right, I think you have done this many times. I think maybe it's too boring now. Is this going to be a helical curve? It's a helix with the radius 2, I mean circle of radius 2 when you look top down, but then it has a stretch. มันยืดออก So it's being stretched or elevated along the z axis. So over here, what are you getting is going to be, okay, let me draw once again. 3-dimensional stuff. Okay, so it's going to be a circle of radius 2. That is radius 2. Okay, but because it's just a cosine t and sine t, it's just a regular orientation. So if you call this one x, you call this one y, you call this one z, it's just going to be a counterclockwise rotation here. But once you add the z component to it, so eventually the final curve is going to look like this. It's going to be right there. Very good. And of course, instead of doing this wow thing, you should just go online and do the 3D plotting software stuff. So you will be able to look at this curve in a nice format and things. So the Cal 3 plot is still a good one that I kind of like used a couple of times. Okay. All right. And what I'm going to show you is using some 3D plotter And the one that I usually use is Cal Plot 3D or Cal 3D Plot. Cal Plot 3D. Maybe I just said Cal 3D Plot. All right, but anyway, so here we go. All right, so you guys can try this. It's a Cal Plot 3D or any plotting software. It works. But this one I kind of like it because, as you can see, there are a couple of options that you can try, and I think this is pretty good for a vector calculus course. I'm not an expert using this software, but it seems like it's easy enough and it's straightforward. For example, for the one that we are using is a space curve. You see that is okay. Sorry, it's a second selections there. Space curve r as a function of t. Perfect. That's our vector value function. And when they select that, now you can have that x component, y component, z component being written in terms of the parameter t. See? So I'm going to use the latest exercise here. I'm just going to put x to be 2 cosine, y equal to 2 sine, and z equal to t. And I'm going to just value the t. So this software allow you to adjust the t. So, and then I can pretty much adjust the value of the t between the range that you want. So if you look at this one, this is the helical structure that I was, the helical curve that I'm talking about. So if I try to orient it in the direction that we're familiar with, give me 1 second here. Woo, it's just so sensitive here. Okay, here we go. I think, is it good? Okay, I think this is good. This is good. Okay, so X is towards you, Y to your right, and Z is pretty much up. So let's focus on the vector. I'm gonna start T equal to 0. See that? Look at the blue curve right there. See? So when I change the T, that is the directions of my vector value function right there. See? So the blue curve, the blue vector tracing the curve, which is in this case is our helical. And if you try to look down along the z-axis, what are you seeing? Of course, you're going to see a circle of radius too. However, this one is like a perspective view of this whole thing. I can turn on the restrict view to 2D here. So this one, there's no perspective mode or anything. It's just straight down along the z-axis. You're going to see a circle. And when I just changing the value of t, see that? You're going to have a counterclockwise orientation of the vector. So the blue vector is just on top, overlay on top of that green vector right there. Cool. Isn't that cool? So let's me start from the negative t again. So I start from the small value of t, and then I just increasing the t. So it just give you that vector is just keep rotating counterclockwise. Okay, and the tip of that blue vector is right on the circle. Nice. All right, so don't forget to try this kind of software. I think it helps a lot with the visualizations of the whole thing. All right, nice. And that looks much better than mine here. Okay. All right, and then from now on, you can pretty much, I hope you try this. I mean, with the software, I think it's going to look much better. Okay, so try these two whenever you like, and I hope you will see what it means by the curve. Oh, but I can pretty much show you roughly if you want. Yeah, so this one, you can see that is flat on z equal to 2. So that means 1, 2. So that means this is going to be a fixed height that's on z equal to 2. And on that height, you're going to have t and t square. What kind of curve is this? What do you think? X equal to t, y equal to t square. X equal to t, y equal to t square. Of course, I can replace this thing back just like when we did in the first lecture. That is just a parabolic curve. Okay, straight. So that's nice. So if I draw this, give you some sort of like line of sight. Okay, let me change the color here. So if I try to use the red, okay, that's my z equal to 2 level, right? Because that is the fixed value of the z, okay? And I'm going to have a parabolic curve along the y. So it's going to look something like this. I think it's pretty good. And of course, this has the direction of this curve is going to be in the same direction that's increasing the x and y at the same time. So it's going to go up in this direction, right? So that direction is just the direction that x and y are increasing along with the t. Cool, I guess. All right. All right. Let's do the last one as well. Okay. Draw a nice one here. So what you can do on the last one, okay, let's do a nice axis here. So on the last exercise right here, I mean, for this one, do I still have one more? No. Okay. Okay. You have x and y to be t and t. So in this case, you can see that these two are the same. So it's just equivalent to x equal to y all the time. So this is just a 45-degree lines on an XY plane. So if you have an XY plane, at least you know that there is something going on along the diagonal line. So let me sort of draw you a diagonal line here. Let me use like a green one here. That's 45-degree line right there. I don't know this perspective looks nice or not, but that is 45-degree on an XY plane. But that's not all we want. What we want is you have a fluctuation along the z-axis that is following the sinusoidal curve sine of t. So that means along this 45-degree angle straight line, the z will fluctuate as a sinusoidal curve. So it's going to go like this. Start from 0, 0. Of course, sine 0 is equal to 0. And you're going to have like, there you go. Not nice. Try again. 3. That's better. Wow, you know what I'm saying here. It's a sinusoidal in three-dimensional space in the sense that it's a sinusoidal curve that's oriented 45-degree on an XY plane, like so. All right, so this is how you trace. Well, it's almost the same as you trace a curve using parametric equations, but instead you represent everything in terms of a vector function. Nice. Cool. So why do I spend so much time with this? The thing of this one is, it turns out I really need some properties out of this. There are some properties that spring out from having representing a curve using the vector. This is going to be so nice. Look at this one. So what if I want to look at the change of the vector value function? Okay. So I'm not going to bore you with the continuity and all this stuff because, of course, common sense, if you're going to have a curve that looks continuous, that means there must be no jump on this curve. So that means everything must be able to trace very nicely. So that means every time you zoom in into any portion of this curve, whatever going on here, then the value of the limit will actually eventually approach 0. That is the continuity, right? You want everything to be continuous. So you assume that the actual value of the function and the value of the limits of that function must have no difference. So it must pretty much converge into the same number. So the difference between the two is going to be equal to 0. So that is fine. But what is so cool about this one is when you look at this limit of the difference, because now we are talking about the vector value function. The first term is vector. Second term is also vector. What does this mean? So let's go back to this figure again. So assuming that you kind of know that, Ajahn, I know that this is the value of the limit of this vector. So I call this vector L to be the limit of this function. So that means this is going to be, of course, one vector. This is your vector L. Let me put a green color on it. But then I want to know what is the limit that try to approach this one. So let me sort of place that here right way. That is the same green, the L, the vector L. But then you have another vector in the form of the vector value function as a function of parameter t. Try to approach this limit. And you just say that, hey, if you say that this function approaching this limit L, the difference must go to zero. That's common sense. You use that from 116 when you try to confirm about the continuity of a function. You just assume that the value of the function approaching the value of the limit and the difference go to zero. The extra stuff that you are getting right now is this. This is not two numbers subtracting each other anymore. This is subtractions between two vectors. And remember, when two vectors subtracting, what does it mean? Okay, let me represent my r of t vector using that purple color. That's already nice. So let's say that is your r of t vector. You're trying to get closer to the limit vector L by looking at the difference between the two. But when you say r subtract by the L, the subtraction, the resultant vector is the vector that point from the terminal vector to the initial vector right there. So let me put it in the red color right here. Whoa. Remember that, right? So that is R, okay? That is minus L is going to be the vector that's trying to point from the L to R. That's what it is. Yeah. And remember that we sort of try to understand this through the difference, the change. This is the change. When I say the change, you can say this is the final, this is the initial. You want to know what is going on between the initial and the final. So you just take the final, subtract out the initial. But for the vector form, it means there must be a vector that representing the change. Let me call the delta. So that is your delta. But the delta is like you go and grab the initial vector, which is the vector L. You grab and then you pull that L into the new position vector R at T. นี่คนทันกันไหม? So every time you want to talk about the change, it's changing from L to R. What is the vector that representing this change? We name it delta. What is going to be the direction of the delta? It's like you ไปกระชากหัวนะ you grab หัว L มาเลยนะป๊าบ and then you กระชากมาที่ R เลยนะ that direction of your pull, that is the direction of the change. อันนี้ภาษาอาจารย์เองเนาะถ้าชอบนะถ้าไม่ชอบไม่เป็นไร but what I'm saying over here is now what are you getting is you get an extra information about the direction. This is the directional change between them and them. See? Cool. Now you have the information about the vector. Okay, and see what does this one go. So with that, so from now on, there is some extra stuff that you have, but in terms of the real operation, look at this. You already represent vector value function as just components functions. You put it in brackets and then you'll be done with. So if you want to take a limit, you just do limit of each component function one by one. If you want to do it 3D, you have X, Y, and Z. If you want to take the limit of this one, you do it one by one. So in terms of the operation, it's simple. Here, I'll give it a try. You are given R as a function of T. Find the limit of this R as T approaching zero. What do you do? I'm doing them separately. Let me use the bracket style, so save some space here. You guys with me? เขียนนาน but it's just like it's like you triple your problems Instead of having the limit of a function, now you have a limit of 3 components. But then you do the limits evaluation term by term, components by components. So you just like, okay, there is a limit of this, followed by the limit of this, followed by the limit of this. You just like do the problems solving, like finding the limits 3 times, one by one. And you can use every techniques that you have learned from 116 to figure out the limits of a function. So first term, you just substitute, it's just a polynomial t squared. So the limit of this one is going to be 0. The second one is exponential, is a continuous function. You can just substitute it in. So it's e to the 0 is 1 as well. Same thing with the cosine. Cosine function is continuous. So you can substitute t in there. Cosine 0 is 1, so it's negative 2. Done. Okay. So finding the limit of a vector values function, that is just so straightforward. You just take the limits of each component of that vector function. Be done with. Okay, so in terms of the operation, that's not too bad. The only thing that is sort of like an additional stuff that you get from this one is, or I just said, is this. There is some directional associated with this difference, the change, the subtractions between two vectors. There are directions associated with it. And here we go. And that leads you to this. You see the similarity that you did before in 116 and here. Back in the 116, you start talking about the continuity, taking the limits, doing the difference, and then eventually that leads to derivatives. The derivatives is just back in the day, the change of the function divided by the size of the change. Let me put it on the side. It looks something like f of x, x plus h minus f of x over h, and then you take the limit of h approaching 0. Okay, so with that, now you're doing the same thing, except you turn that just a function into a vector. Woo! And as you can see, what you are trying to do is just finding the limit. So that means you just have to do the limit of each component of the vector one by one. So in terms of the operation, Adan, I can do it. I can figure out the limit in x components, in y components, in z components. But the only thing that's going to add on top of this one is what? There is some direction. So cool. So with that, this is the definition of the derivatives of a vector. เจ๋งมะล่ะ? Okay, so finding the derivative of a vector is going to be simple as you take the derivative of each component one by one. Because in the nutshell, it's just taking the limit of this one, and then we just talk about finding the limits of the vector values function to be just finding the limits of each component. So doing the derivative, ทุกคนบอกเลยว่าเฮ้ยอาจารย์เดี๋ยวwe'll come back to this เนาะ we just say, hey, find the derivative of this. What are you going to do? อาจารย์ไม่ได้หาเรื่องนะดูน้ำเสียงเหมือนกวนๆนะ so they say, hey guys, give me the derivative of this function. You do the derivative component by component. Seriously. You take t square, take derivative. That is your x components derivative. You take the y component, e to the t, do the derivative. That is your y component. And then you take the z component, do the derivative. You're going to get the derivative in the z components. That's it. So your answer will be differentiate t squared, you get 2t. Differentiate exponential t, you get e to the t. Derivative of the cosine, you get negative sine. Okay, don't forget the constant in the front too. Cosine, you get negative sine. Negative turn positive. So I just get rid of that positive sign. And don't forget the chain rule. You have to differentiate pi t, you get extra pi here. So let me put it in the front. Done. So once again, no matter it is the limits or derivatives, all you need to do for the vector function is just you do it components by components. Whatever that you have learned in 116 or in whatever calculus back in your high school day can be performed here again. Only do it triple time. ทำ3เท่า x, y, z. And all of the rules of differentiation works here. Derivative of a constant equal to 0. So now if you have a constant vector, you're supposed to get a 0 vector because you get 0 in all components. If you multiply a vector by a constant, you can pull the constant out and then do the derivative later. No problem. You have the summation or subtraction between two vectors. You can add them or subtract them, then do the derivative. Or you can do derivative first and then add or subtract later. Doesn't matter. This is just derivatives. So it's a linear operator. So you do it before or after has no effect. Now you have a product. Don't forget, we don't have the product between two vectors. Well, we do have, but you cannot just say product, right? You have to specify it's a dot or it's a cross. So this is not the case. So this is just a function, which is a scalar function, multiplied by a vector function. So don't forget, we are not doing vector multiplied by vector yet. This one is just scalar and vector. So if this is just a simple scalar multiplied by the vector, you can do a b a db plus bda if you want. หน้า ดิบหลัง บวกหลัง ดิบหน้า yeah? All right, so you do the front derivative of the back plus the back derivative of the front. So the product rules still work for this derivatives rule. So in terms of the operation, it's no problem. So the only thing that I would like to emphasize here is what? Direction. Look at this. You have the R. You move it to R plus T. I'm sorry, T plus H. So you have R at T, and then you adjust T a little bit. So that is your change to a new value of the T. You increase the parameter T by a little bit, H. Of course, these two vectors will point in a different direction, doesn't really matter. But what is the change? The change, you take the new, subtract the old, okay, the final minus initial. And we already learned that the direction of this change is going to be from where? From the old to the new. You grab the head of the old right here, and then you drag it to the new position here, which is there. So the directional change is going to be this direction right here. Bam. You guys with me now? You know, every time you see this, that is your change. Now, by definition of the derivative, you need this change to be super, 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 super small, approaching 0. So what does it mean? It means this change, this edge, you're going to move just a tiny bit of it. Look at the next figure here. If I try to move this by just like super tiny, so actually the vector is going to move by just a bit. So I'm just going to do this here. Here, guys. You guys with me, right? So this is R at T plus H, but H is so super, 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 super small. Zooming in, zooming in, zooming in. So that change is going to point with me. So what is the direction of this change, guys? Yeah, everything is super, super, super small until it's infinitesimally small. It's approaching 0. So that change right here eventually is going to be here. Look at this. The original direction in that direction, the direction of the purple here is in this direction right there. You see what I'm trying to say here? So these two are perpendicular to each other. And that is the conclusion here. Whenever you find the derivative of a function, if that function is the vector values function, the derivative is another vector, right? Of course. But the direction of the derivative is perpendicular to the original function right there. Or, of course, if you want to say, hey, Dan, we have been talking about the tracing of a curve. Of course, every time that you have something that is perpendicular to the R, you can think of R as the radius of curvature. Yeah? รัศมีความโค้ง yeah? Everything that is perpendicular to the radius is going to be the tangential direction. So that means the R prime, the derivative of the R, is going to be tangent to the curve. ชี้ตามแนวเส้นสัมผัสความโค้ง Wow, very cool. And that's why it say, here we go, R prime, the derivative of R, is tangent to the curve at points in the direction of increasing parameter. Cool. All right. So this is the whole conclusion I want to make. If you go back to our not simulation, it's our plotting again, you will notice that actually in this tracing right here, the blue that's pointing from the origin to the curve, that is your R, right? And when I try to increase the T, that curve is rotating counterclockwise. But now you notice that is the black vector. That black vector on your right hand is the derivative of the blue vector. And it's perpendicular to the blue. Or if you think in terms of the curve, the blue vector tracing a circle. So the black is tangent to the curve. I can turn everything in 3D if you want, because everything has to be perfect in 3D. See that? So when I look at the black vector, the blue vector is curving up. And the black vector is always perpendicular to it, no matter where it is. So let me change the angle a bit. Here we go. See that? The black vector always perpendicular to the blue all the time. All right. And don't ask about the green just yet. All right. But I think some of you have already noticed, but Ajahn, there is also the green vector. Actually, the green vector, well, I have to talk about that or not. But anyway, the green vector is the derivative of the black one more time. It's just this plot just give you the second derivative of the blue. So that means the green must be perpendicular to the black again. But because this one is tracing a circle, so that's why the green is just right on top of the blue if you look top down. But for the overall effect right here, so that's why the blue is pointing outward from the origin. The derivative of the blue is the black, which is perpendicular or tangent to the circle. But then the derivative of the black give the green point backward to the center of the whole thing. So good. Nice. So that is the property of the derivative of the vector values function. The derivative, of course, the operation is now simple. You do it component by component. But the interpretation in terms of the direction is the derivative of a vector give another vector, the derivative vectors, that is perpendicular to the original vector, or say is tangent to the curve that is being traced by the original function R. Very nice. Okay, but if this is not sort of like convincing enough, let me give you one more thing. If you like this, if you don't like this, that's okay. If I really call this vector R to be my position vector, because R give me the whereabouts of my, let's say this is my object. All right, there is an object there. It's placing at the position of the terminal point of this vector r. I take the derivative of this. What is this? The change of the position with respect to t. If I say t is time, this is your velocity vector. Of course, we learn from physics. The velocity vectors always point in the tangential direction to the path that the mass is moving. Not only that, I can do the v prime again. What do you get? You get the acceleration vector. But then everyone know every time that things move in a circular fashion, there will be what? Of course, a centripetal acceleration ความเร่งเข้าสู่ศูนย์กลาง All right. So that means the derivative of the v that's giving you the green. And that's why that's complete the whole picture in the Cal plot 3D that you just saw over here. The blue give you the position vector. Derivative of the blue give you the black, the velocity, which is of course velocity has to be tangential to that circular motion over there. But then when you do the derivative of the black, which is velocity, you get acceleration. But everyone knows the circular movement has the centripetal acceleration ความเร่งเข้าสู่ศูนย์กลาง so that's why there is a green vector pointing towards the center. That is your acceleration of a circular motion. All right, so I hope this give you some connections. But after this, wow, man, things is going to be very easy because operation is very simple. And now you can combine this with things that you have already learned in the past. For example, you want to find tangent line to a graph that being traced by vector value function. Then you can do it now. So let me ask you this before you look on the right side of this whole thing. If I have a curve, the blue curve, wham, this blue curve being traced by some vector value function r. Okay, now I'm asking you, but hey guys, give me the tangent line. I want the straight line that is tangent to this curve at point P. How would you do it? จำได้ไหมทำไง When you want to trace a curve, what do? You need a point and a directional vector. ทุกคนจำได้ไหมอยากจะลากเส้นตรง1เส้น Give me a point and direction that you want to go. If you have a point and the direction, all you can get is just I'm going to draw a line through that point P in the V direction. See, you need a point and the directions. This is it. The point is already be given here. You say, hey, I want to figure out what is going on at point P. So you already pinpoint where you want to find the tangent line. All you need is just, hey, which is the direction of the tangent line? Of course, it has to be tangent to this line because that is a tangent line. But to get to this tangent direction, all you need to do is just find its derivative. Because we already said that the derivative is just the vector that tangential to that curve. So that's it, guys. Okay, so you take R naught, that is just the vector that point to the point that you want to figure out the tangent line. Then you have the directional vector, which is coming from derivative of the r at the point P. Once you have this point and the directions, you just multiply by the parameter t, you get a straight line. You're done. เฮ้ยง่ายเปล่า Cool. All right, so now having a straight line is now going to be super simple. Get a point, get the directions, take the t, parameter t, multiply by that direction, add it on top of the starting point. You're done right here. Okay, nah? Cool. All right, so now let's give it a shot. You are given a parametric equations. See, find the tangent line, which is a parametric equation of the tangent line to the circular helix. We have done helical curve so many times today, and this is going to be one more time doing that, where t equal to d0 is given to be just like a general representation of any point or any value t. Or they say, hey, or you just put t equal to pi or whatever. It doesn't really matter now where. All right. So you can just say find this equations of the tangent line at any time t or at any value of the parameter t. Okay. So how would you do it? Okay, go ahead. You just say, Ajan, no problem. I'm writing a vector value function. So let me use a bracket style here. It's the cosine t in x, sine t in y, and t in z. So that is my vector now. Okay, what is my original point that I want to evaluate? We name that R naught. That is your starting point. So it's just R at some initial time t or initial parameter value t naught. So all you get to do is just substitute that value of the t in there. That is your starting point จุดเริ่มต้นของเรา so once you have the จุดเริ่มต้น starting point, now you want the directions. Which direction you want to go? You want to go in the tangential direction, right? So you're going to get the tangential direction from r prime. Okay, so first you figure out the r prime first, and the operation is simple. Do the derivative component by component. Derivative of cosine, you get sine. Derivative of sine, you get cosine. Derivative of t, you get 1. Now you want to evaluate at exact same point. So I want to figure out the r prime at t0 as well. So all you need to do is just substituting the t with the t naught. So you're going to get negative sine t naught, cosine t naught, and 1. So far, so good. So what is your straight line, guys? Straight line. So your straight line is going to be exact same as this one. R naught plus T V naught. Go for it. So your straight line, just R. Well, we're just using the same value. I mean, same notation R. So it's going to be T naught. I'm sorry, R naught right here. So that's going to be cosine T naught, sine T naught right there, which is very good. Okay. And then what else that you're going to get here? Plus, very good. Then you put the parameter t in there. Bam. And then followed by that r prime at t naught. Done. All right. And then you can spread them out, talking about the x component. So you can say x is going to be, just take the x component here. Bam, bam. So it's going to be cosine t naught. Okay. Minus t sine t naught. And then you do y component. You take bam, 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 bam. So it's going to be sine t naught plus t cosine t naught. Very good. And then you do z component. Z is going to be t naught plus t. That is your straight line parametric equation of the tangent line to this helical curve. And then if you really want to figure out what is going on at pi, you just substitute t naught with the pi and then you're done. Yeah, not too bad. Okay, so from now on, whenever you want a straight line, you just need the starting point right there and the direction that you want to go. If you get these two, all you need to do is just multiply this by the parameter t. Starting from point P, you go ahead. You move your point along the V direction. Then you're going to trace a straight line. But now, for today's lecture, your directions that we're talking about is the tangential direction. And we're going to get that direction by simply do the derivative of the position vector. พอรู้เรื่องไหมอ่ะพอได้เนาะ Okay, so I hope this is all right. Okay, so if this is good, then we almost done, guys. This is going to be quick. The rest of the business that we're going to do is just, well, you have already done with the limit, differentiation, derivatives. Why not the integration? Right? So, if you really want to integrate a vector values function, what is going to happen? Correct. You do it components by components. So that's pretty much nothing sort of surprising anymore at this point. So let's try example 6. If you are given R, a function, the vector functions here, then, and if you want to, hey, let's do the integral, what will happen? All right, so let's give it a shot. So I'm going to say integral R of t dt. Now, well, I can show you some definite integral. I can set like a lower limit and upper limit, whatever. So let's do like from 0 to 1. That will be fine. Okay, so all you need to do is just do the integral component by component. So what it means is in the x direction, I have to integrate t squared dt from 0 to 1. In the y direction, I have to integrate e to the t dt from 0 to 1. And the z components, I have to do the integral of negative 2 cosine pi t from 0 to 1. So it's like 3 for the price of 1. Right? Asking you to do one integral, but it means you have to do 3 times for each component. But that's, I mean, for this, it's quite all right. So you just say it's going to be 3 cubed over 3. Take the limit from 0 to 1. And then for the second one is exponential. This is okay. The integral of exponential, you get exponential. And the last one, you have the 2 right there. But the integral of the cosine is just sine. So the negative is still there. But then don't forget you have the pi t. So that means you have to divide it by pi to get it out. So just don't make sure that you checked all these factors and everything's supposed to be correct this way. Oh, forgot to put the limit there from 0 to 1. All right. And then by just substituting the upper and lower limits, and you are pretty much done. It's 1/3 for the first component. Is e minus 1 for the second. And psi pi is 0, psi 0, 0, 0. Okay, very good. So that's it. So that is your integral of this vector. You do it one by one. So with this, without a surprise, you have the rules of integration that worked before is going to work again. You multiply the function by the k. You can do it before or after integration. That's fine. Summation of the two, you sum first and then integrate, or integrate first and then sum later. That is fine. All right. So from this point on, everything works just like before. You do it component by component and you are done. So let's complete this final slide together right here. All right. Today is quite all right. Okay. Example number 7. You do the integral of this whole thing. You do it component by component right there. Okay. Now, this is like sort of indefinite integral, Do you have to worry about this? Well, no. Every time that you do the integral of just like a real function, you always have to add arbitrary constant ค่าคงที่ใดๆ right? So why not? Over here, you just have to add that arbitrary constant on each component. So at the end, you're going to get arbitrary vectors. That is your C right here. So that's no big deal. So let's do that integral term by term. You're going to get t squared. Okay, let me use ij notation just to change the mood a bit. And then you do the integral of 3t squared. You're going to get t cubed j. And then you just say some extra arbitrary constant, something like that. Arbitrary constant z. Just put it there. Okay? That works just like before. Okay, try again. Example 8. If you have a definite integral, that's even easier. And actually, this is just exactly the same function as the example 7. So actually, I can say is 2 square I plus t cubed j. But then I just have to do it with the limit of integration. So I just put it there. There you go. So with the definite integral, you don't need that arbitrary constancy anymore. And that gives you 4i plus 8j. Pretty good. All right, try again. Find r of t given that the derivative is 3 2t and there is some condition that r at t equal to 1 is 2 5. ทำไงดีจ๊ะอันนี้ Of course, to get back to the r from the information about the derivative, you have to do the integration. So go for it. So what you have over here is the r of t is going to be the integral of the r prime dt. You guys with me? All right. And because for this problem, you don't have the limit of integration just yet. So you have to do like an indefinite integral for now. And then you're going to add some arbitrary constants. But that arbitrary constant is going to be evaluated through the condition given right here. So let's see what I'm saying over here is this. So I'm going to do the integral first. So I'm going to do the integration of 3 to t dt. I'm doing the integration component by component. I'm going to get 3t and 2 square. You guys with me? Plus any arbitrary constant. All right. And what is this constant? Well, then no problem. I have this information waiting for me right here. It says when t equal to 1, the vector is going to be from the upper line here. When t equal to 1, oops, sorry, I put t equal to t here, sorry. T equal to 1, I just substitute 1 in there. So I'm going to get 3, 1 plus c, right? That's from the upper line there. But the information said this must be equal to 2, 5. So from this, I can figure out the components of the z one by one as well. So my vector c itself is going to be 2, 5, subtract out the 3, 1. So it's going to be 2 minus 3, 5 minus 1. So it's going to be my negative 1, 4. Wow. And that's it. I can just plug this thing back in here. So my grand conclusion is r at any parameter value t is going to be 3t plus t squared plus my vector c that has already been evaluated using the information given right here. And that's it. I'm done. Oh, I think I'm supposed to put just the comment here. There you go. So it's going to be 3t minus 1 for the x component and t squared plus 4 for the y component. That's it. So I think that's good. All right. Not bad, I guess. Already. So if this is good, then that's it, guys. Done for today's lecture. Okay, very good. So, as I said, so these are partial derivatives. The lecture 7 is supposed to go after the midterm. So I'm gonna distribute the handout, the second half of the handout, using this, and then I'm gonna change the numbers into lecture number 8. All right. So next time when we see each other, then we're gonna do the review for the midterm. That will be our lecture number 7. Okay. And before that, I'm going to release the exercise, which is the material for the lecture number 7, the practice exercises for the midterm. All right. And then you can, spend some time try solving those problems. And then when we meet again next week, then you can come with your questions. Or if not, then I can show you some of the problems there. Okay. Sounds good? All right. So if this is good, then that's it, guys, for today's. Thank you for sticking around. And I will see you again next week. Have a good week. Bye bye.